So thanks for showing up for class. Let's make it worth your time. And I wish you all the best with your upcoming tests this weekend. Today, we are getting very close to finishing up 3.5. We'll see how close we get. Hopefully we will, starting chapter 4 next week. Topic 3.5, I will admit, is a little uncomfortable. It's probably a newer topic, if not completely new to you. And it feels perhaps like taking a roller coaster. Like you're like, I just figured out VSEPR, hybridizations, bond angles, Lewis structures, and now you're just taking me for a loop and now saying we have molecular orbitals on top of all of this. Molecular orbitals are needed because the previous theories aren't sufficient to explain all the phenomenon that we see. We know we have resonance structures, and valence bond theory didn't do justice to explaining that. We have species that are paramagnetic and diamagnetic, unpaired electrons, paired electrons, and we can't fully explain that with our current theories. So now we move to molecular orbital theory, and this is what we currently use in chemistry when we're calculating energies of molecules and colors and electron transitions. This is the theory that we use. We're introducing you to the first bite-sized piece of this theory. For this course, we're only going to be looking at diatomic molecules. So that means two atoms stuck together. And homonuclear, so two atoms that are the same, so fluorine, fluorine, hydrogen, hydrogen, and so on. It gets more interesting when you mix up the types of elements and when you have larger molecules, and you can study that, and it's really cool, but we're just going to do the first piece of it with homonuclear diatomic molecules. Feels a little bit like a roller coaster because it's a little uncomfortable, it's a little crazy, but I promise you we will land this, and you will be able to understand the concepts that we need to be able to apply. So we know that electrons can behave like waves. We know about atomic orbitals and wave functions of electrons in s, p, d, f orbitals. And now we're going to translate that knowledge to molecular orbitals, orbitals that apply to the whole molecule. And for this topic, we're making the molecule only 2 atoms big, keeping it nice and manageable. So the first molecular orbital that we introduced you to last class was when we have a 1s atomic orbital and a 1s atomic orbital combining in phase. So that means positive phase and positive phase, or negative phase and negative phase. They're undergoing constructive interference. We're bringing these 2 separate atoms together into the same space, and they make a new orbital, a molecular orbital. So that's called an MO, a molecular orbital. It's called a bonding orbital because when electrons are in this orbital, they're promoting bonding. They're promoting keeping these 2 nuclei together, sharing those electrons. This is a constructive combination, and we end up having more electron density, keeping these 2 atoms together. When atoms combine and form a new molecular orbital on axes between them, it's called a sigma bond. And that's why we have that little sigma symbol with the subscript 1s. And this is a bonding molecular orbital. Well, we can combine these out of phase. So a positive and a negative, or take 2 positives and you subtract them, right? But now we have 2 opposite phases coming together, and we are forming an anti-bonding orbital. We have a new node forming between the 2 nuclei. We have a region where electrons are not going to be found. So the red and blue ball looking thing here, it's 1 molecular orbital, but it has a node. It's a nodal plane directly between the 2 nuclei. And this is promoting molecule destruction. It's not combining those 2 atoms. When we have electrons in an anti-bonding orbital, it's like pushing those nuclei apart. This is called destructive interference, and it gets this little asterisk, that little star that tells us it's an anti-bonding orbital. A new node was formed when this molecular orbital was created. The little subscript tells us it's from 1s atomic orbitals, making an anti-bonding sigma 1s orbital. So let's take this a step further now. So we have a bonding orbital and an anti-bonding orbital. Both of them are sigma orbitals, so they're combining on axes. The bonding orbital, when these two atoms come together and make a new orbital and they're in phase, constructive interference, the new molecular orbital is more stable than the two starting atomic orbitals. So the energy of the molecular orbital of the sigma 1s orbital is stabilized. It's lower in energy. In contrast, the anti-bonding molecular orbital is higher in energy. That new node has formed. This is not as stable in energy for electrons to be in, so it has a higher relative energy. So we draw these molecular orbital diagrams. We have energy on the y-axis. We have atom 1 on the left-hand side, and it looks like we're combining this for hydrogen. Actually, I'll jump back to this one because you still have the picture of this one. Here we have two separate hydrogen atoms, one electron in a 1s orbital for atom 1, one electron in a 1s orbital for atom 2. We combine them together and we form this sigma 1s bonding molecular orbital and a sigma star anti-bonding orbital. The electrons are going to go into the lowest possible energy orbital, and so they go into the bonding orbital, and this is how we get dihydrogen, or H2. So this is the pretty picture version. This is how we would actually draw it if we were communicating a molecular orbital diagram. So it just means the cool orbital pictures aren't included. We usually put one atom on the left, one atom on the right, and then we put the molecular orbitals in the middle. And we show the relative energies of these molecular orbitals. So we could draw this for H2 for diatomic hydrogen. Each one has a 1s electron in atomic orbitals. When they come together, we get our sigma 1s bonding molecular orbital and our sigma star 1s orbital, our anti-bonding orbital. And we can see it's higher in energy and lower in energy. When we want to place the electrons, we follow all the rules that we know so far, and we count up the total number of electrons. Here we have 2 total electrons to place. We start putting them in the lowest energy available orbital, which is our bonding orbital. That leaves our anti-bonding orbital empty. So the 2 electrons in dihydrogen are promoting bonding. They're promoting keeping these 2 atoms together. We don't have any electrons in the anti-bonding orbital trying to push these 2 atoms apart. Now we label different molecular orbitals so that we can talk about energy transitions, and it's important for colors and things like that. So we have the HOMO orbital, the highest occupied molecular orbital. So we find this by looking at all the options. Here we only have 2, it's nice and simple. We find the molecular orbital that's highest in energy that has electrons in it. And here we can see our sigma 1s molecular orbital we can classify as the HOMO. It's the highest occupied molecular orbital. Now that's in contrast to the LUMO orbital. This is the lowest unoccupied molecular orbital. Again, it's nice and simple. We only have 2 options. But if we had like 10 options, we'd start at the top, highest energy, the empty ones, and work our way down until the lowest energy orbital that's still empty. So it doesn't have any electrons. Why does this matter? Well, electrons often jump from the highest filled to the lowest available. So that energy transition is important for colors and conducting electricity as well. So here we have our orbital diagram. We need to be able to draw these, we need to be able to fill them out, and we need to be able to interpret them. So we're going to be working with these today. So now we're ready to get into the finer details of the molecular orbital theory, now that we have the 1s orbitals, the bonding and the anti-bonding under our belts. So first thing, the number of atomic orbitals that we put in is going to be the same as the number of molecular orbitals that we get out. In this example with dihydrogen, we put in 2 atomic orbitals, 1s and 1s, and we get 2 molecular orbitals, a bonding and an anti-bonding. Number 2, the relative energies we can predict somewhat. We always know that the bonding molecular orbitals are lower in energy than the anti-bonding molecular orbitals. The anti-bonding molecular orbitals have a new node, a new region where electrons aren't going to be found. These ones promote destroying the molecule. And orbital filling, number 3, we just have to follow all the rules that we learned for atomic orbitals. So when we're filling electrons and putting electrons in these molecular orbitals, we follow the same rules. So that means we start at the lowest energy, the most stable available orbitals. We fill those up and go up in energy as we do that. We can put up to 2 electrons in a molecular orbital, and they're going to have opposite spins. So an up spin and a down spin. So a plus half and a negative half. And if we have 2 orbitals that have the same energy, we haven't seen that yet, but that's coming up today. When there are degenerate orbitals, we half fill them, and then we fully fill them. So this is the same thing that you've already learned. And principle 4 is important when you move further beyond this course, but molecular orbitals form best when they're coming from atomic orbitals that have about the same energy. So a 1s and a 1s, those have exactly the same energy, and they form really good molecular orbitals. When we start working with atoms that are different elements across the periodic table, the 1s orbitals might have different starting energies, and it gets a little more interesting, but that's beyond the scope of our course. So the best overlap happens when atomic orbitals have the same energy, but for our course, all of them will have the same energies. Yes? Great question. So can we review number 1, the number of atomic orbitals equals the number of molecular orbitals? You are correct that hydrogen only has 1 1s atomic orbital. But when we're forming H2, we have a 1s orbital from atom 1 and a 1s orbital from atom 2. So that's how we get 2, because we have 2 atoms. If we only had 1 atom, I agree, there would only be 1 atomic orbital. But we have a 1s from atom 1, a 1s from atom 2. They come together and they can come in phase, constructive, lower energy, or out of phase, destructive, higher energy. That make sense? Great question. Thank you. Okay, so when we're filling out these molecular orbital diagrams, when we're putting electrons in these orbitals, we can also determine bond order from the way the electrons are placed. So we need to learn how to interpret what this means. Bond order is important because it tells us if we have a single or a double or a triple bond, or as we know with resonance structures, we could have a 1.5 bond or a 2/3 bond. You can get some funky fractions in here as well. In addition to figuring out the bond order, the number, the magnitude, from that bond order, we can also figure out if that molecule exists. If the bond order is 0, then that molecule doesn't exist. The net pull of having bonding molecular orbitals and the net push from having anti-bonding molecular orbitals equals out, and there's no net attraction between those atoms. So if we have a bond order of 0, hypothetically we could write it on a paper, but in reality it does not exist. And so it's also important to determine if a molecule exists from the bond order calculation. So nice simple formula. You can derive it yourself. Bond order is simply the number of bonding electrons. So electrons that are in bonding molecular orbitals compared to finding the difference between the number of electrons in antibonding orbitals. We want to find out the difference. Is there a net pull holding these two atoms together, or is there a net push pushing these atoms apart? And then we divide by 2 because we know we need 2 electrons to make a single bond. So every pair of electrons is going to increase that bond order. A single bond has 2 electrons, a double bond has 4 electrons, a triple bond, and so on. So for hydrogen, we can look at the molecular orbitals. So we're looking at this middle region now, and we can count up the number of electrons in bonding orbitals. And I can see we have 2 electrons in the sigma 1s bonding orbital. I'm going to subtract that from the number of electrons in the antibonding orbitals. Here, it's 0. We didn't put any electrons up there. And we divide by 2 because 2 electrons makes 1 bond, or 1 bond order. 2 divided by 2 is 1, and this matches our understanding of dihydrogen. If we drew out the Lewis structure for hydrogen, that's what we would draw, and it's the same prediction that we get from molecular orbital theory, which is great. Okay, so now let's do a few more examples filling out these molecular orbital diagrams. We're only working with the first period of the periodic table at this point. So basically hydrogen and helium. So we want to use these molecular orbital diagrams and predict whether these 3 species can exist. So what does that mean? Well, is the bond order greater than 0? Does it at least have like a half or a 1 bond order to hold these together? So let's work on filling these out together. So we're going to start on the left, and we're going to start with H2+. Here you have the framework already drawn out for you, and we do provide you with the framework on a test or an exam, but you need to learn how to fill it out and how it was constructed. Okay, so H2+, how many electrons and how many elements, what do we have? Well, that means we have a hydrogen, and one of them is going to have a charge. One of them has lost an electron. I'm going to count up the total number of electrons in H2+. Each hydrogen should have 1 electron, and I have 2 of them, but it's H2+. That means we've lost 1 electron. So 2 minus 1 is 1. So we're starting with 1 electron. You could draw it on the left or the right, I don't really care. One of the atoms is coming with an electron, and one of the atoms is not coming with an electron. So that means we have a total of 1 electron to place in this molecular orbital diagram. It's like the simplest thing we could come up with. So total number of electrons is 1. We start at the bottom, lowest energy of our molecular orbital options, and we place it in the sigma 1s bonding orbital. That's how simple that one was. And then we can calculate the bond order. So the number of bonding electrons in bonding orbitals is 1. The number of electrons in antibonding orbitals is 0. Divide by 2, and we get a bond order of 0.5. So if you ever come across H2+, you can predict that it has a 0.5 bond order, so less than a single bond for strength. Now let's move to He2+. Helium, if it was neutral, would have 2 electrons. We have 2 of them, so I would expect 4 electrons, but it has a positive charge, so that means 1 electron has been lost. So we have a total of 3 electrons to play with in this species. So I'm starting with a helium on the left and a helium on the right. They each have a 1s orbital. One of them started with 2 electrons, one of them started with 1. I have a total of 3 electrons to place. I'm going to start at the bottom of my molecular orbital energy options and fill upwards. So 1, 2, and 3. The 3rd electron went in our antibonding orbital. So now we can calculate the bond order. So I have 2 electrons in bonding orbitals. From that, I can subtract 1 electron in an antibonding orbital. That gives me 1 divided by 2, which is a bond order of 0.5. So this bond order strength is going to be less than a single bond. And finally, let's do He2. So we have helium atom 1, helium atom 2, and they're both neutral, making a neutral molecule. So each one is starting with 2 electrons. There's 2 of them, so that tells us we have a total of 4 electrons to place in this diagram. So I'm going to start at the bottom. 1, 2, I filled up my bonding orbital, and then 3, 4, I have also filled up my anti-bonding orbital. So we have 2 electrons pulling these atoms together, and 2 electrons pushing these atoms apart. So when we go ahead and calculate the bond order, we have 2 electrons in a bonding orbital, and we have 2 electrons in an anti-bonding orbital, and we divide it by 2. So 2 minus 2 divided by 2 is 0. A bond order of 0 tells us that He2, the molecule, does not exist, DNE. And remember, helium doesn't form bonds. It's a noble gas, and it's really small. It's not like one of those really large noble gases. It doesn't form bonds with other helium. So He2 does not exist, and molecular orbital theory can tell us that. Why? Well, the 2 electrons pulling it together are counteracted by the 2 electrons in anti-bonding orbitals pushing it apart. No net pull. These atoms don't form a molecule. Okay, so whether we have electrons in bonding and anti-bonding, we now know how to place these electrons, at least for really small atoms. Whether the molecular orbitals have all paired electrons or whether we have unpaired electrons is going to help us figure out if a species is paramagnetic. That means it's attracted to a magnet. We covered this earlier when we first introduced this topic. Or if it's diamagnetic, it is not attracted to a magnetic. Remember that that attraction has been killed. That's how I remember it. So a paramagnetic species has a non-zero net spin. That means we have at least 1 unpaired electron. If we added the plus half and the minus half and the plus half, the sum of all those spins is not 0. So we have an unequal amount. We have 1 or more unpaired electrons. That's in contrast to diamagnetic species that are not attracted to a magnet. Why? Well, they don't have a non-zero net spin. Sorry, let me rephrase that. They have a 0 net spin. For every up half spin, they have a down spin. So the net sum of all those spins is 0. All the electrons are paired. When we're looking at molecules, we need to look at the electron placement in molecular orbitals. If we're looking at atoms or elements that aren't in molecules, we look at the electrons placed in atomic orbitals. So iron is a material we're probably all familiar with. You probably played with some magnets when you were a kid, and perhaps you still do because that's kind of fun. Iron, as an atom, as an element, has a whole bunch of unpaired electrons, and we've already learned how to write out this electron configuration. Because of all these unpaired electrons, it has a non-zero net spin. It can interact with a magnetic field. It's attracted to a magnet. Iron is paramagnetic. So we can look at its electron arrangement in atomic orbitals and predict that it's paramagnetic. So we're going to continue on paramagnetic and diamagnetic, looking at atomic orbitals. Then we're going to come back to paramagnetism, diamagnetism for molecular orbitals. So it's kind of like a little bunny trail about paramagnetism and diamagnetism using atomic orbitals. So let's start with chloride. A nice trip back down memory lane. If we are writing out the electronic configuration for chlorine, we would write out neon and then 3s2, 3p5. But if it's chloride, that means it has gained an electron. And now I'm going to draw out the electrons in 3s and 3p orbitals. We still have 2 electrons in 3s, but we now have 6 electrons in our 3p orbitals. We singly fill, and then we doubly fill. So chloride has a total of 8 valence electrons. All the electrons are paired, therefore it's diamagnetic. So I'll leave that up on the screen, and I'm going to ask you to do the next one. Cadmium 2+. Is it paramagnetic, diamagnetic, and why? So chat with the person beside you, write out its electron configuration, orbital diagram, and figure that out. And 10 more seconds. And 3, 2, and 1. Okay, almost 3/4 going for B. I agree. It's diamagnetic because all of its electrons are paired. That means it has 10 electrons in the 4d orbitals. Remember, when something becomes a cation, it loses electrons in its highest energy atomic orbitals. Those are the 5s electrons that are removed, which means we keep all 10 4d electrons. They're all paired. Therefore, cadmium 2+ is diamagnetic, and it is not attracted to a magnet. Okay, so that's our slide little bunny trail comparing this to atomic orbitals. Now let's go back to our conversation on molecular orbitals. These are the diagrams that we just filled out, so you might just want to flip back a page rather than redrawing this. When we did H2+ and the other species, we figured out their bond order, we drew out their molecular orbital diagrams, and now we get to go back and say, well, are they paramagnetic or diamagnetic? So let's start with H2+. It has 1 unpaired electron, therefore it must be paramagnetic. He2+ has 2 paired electrons, but 1 unpaired electron. Unpaired tells us that this is also a paramagnetic species. In contrast, He2+, all of its electrons are paired, so it is diamagnetic. But in reality, it does not exist, DNE. So Is it diamagnetic? Doesn't exist anyway. But hypothetically, all its electrons are paired. Okay, so what we've done so far is taking a 1s orbital from one atom, a 1s orbital from another atom, and bringing them together to see if we get bonding and anti-bonding. We're now going to extend this discussion to second period elements. We're continuing on with diatomic, so only two atoms coming together, and homonuclear, so two identical atoms. We're not going to be mixing nitrogen and oxygen. That's going to happen next year instead. So we're going to look now at combining the valence electrons in our second row of the periodic table. So now the valence electrons might be in 2s orbitals. So imagine we have a 1s orbital, but then the 2s orbital is actually what engages in bonding, the valence electrons. So we could have one atom with a 2s orbital and another atom with a 2s orbital. And just like we did when we had 1s orbitals, two atomic orbitals, one from each atom, makes two molecular orbitals. A bonding molecular orbital lower in energy, an anti-bonding molecular orbital that's higher in energy. They're combining on axes, just like we did with the 1s, but now they're just bigger. So just imagine these balls are bigger, combining on axes to make a sigma molecular orbital, and combining with destructive interference out of phase, making a new node between them, which makes this an anti-bonding orbital. But you can see it looks very similar to sigma 1s and sigma star 1s orbitals. It gets more interesting though once we move to the p orbital combinations. So we've already figured out the s orbital overlap. Now let's think about atom 1 and atom 2, and we're going to bring them together. But now we're going to think about the px, the py, and the pz. So my question for you is, based on this sketch, the x, y, z axes are drawn in, so use those coordinates. Based on this sketch, which orbitals could form a sigma type bond between atom 1 and atom 2? Chat with the person beside you for like 30 seconds and make your prediction. And 10 more seconds. And 3, 2, and 1. Okay, we're quite split here. That is interesting. Maybe it's just really small to see, which would be fair. I'm going to go with E as the correct answer. Popular by just a little bit, meaning px and px. If we bring atom 1 closer and atom 2 closer, remember that a sigma bond is when we have that head-on overlap. We have the x-axis is the on-axis between the two nuclei that we're bringing together. As we do that, so let's imagine one. Here are p orbitals from atom 1 and atom 2. The px orbitals are on axes and hitting head on. That's in contrast to py in this picture and pz. They're pointing away from you. So the px orbitals are coming into contact head on, And we know that head-on means that we're talking about a sigma bond. The definition of the sigma bond didn't mean as much when we first introduced it, but now when we're talking about head-on versus side-on, we can see there is a difference indeed. So let's take a look at these options here. When we're combining on axes, the axes between the two nuclei, I'm going to start at the bottom here. The bottom of this image is constructive combination. How do we know it's constructive? Well, the lobes that are coming into contact with one another are in the same phase. So they're both positive phase or both negative phase, doesn't matter, they're both the same phase. So as they come into proximity, just like my eggs over here, they can form a lobe that combines and have a new molecular orbital that we classify as a bonding molecular orbital because they combined in phase. When electrons are in this bonding molecular orbital, they're holding those two nuclei together. The little dots are the nuclei. So atom 1 and atom 2. And we call this a sigma because we combined it head-on, and we call it 2px. We call it x just because the way we drew our coordinates, it shows it's combining on x. If we drew it combining this way, then so be it, call it z, whatever. But they're coming from the 2px when we're combining them along the x-axis. Now that's in contrast to our destructive combination above it, when we can see that the opposite phases are coming into contact with one another. They don't merge like Play-Doh, making a shared space. We have a new node being formed as these are brought into proximity. So now we're combining them out of phase, and a new node is going to come into existence. So these do not want to come into contact with one another. They kind of squish down, and a new node, a new region where electrons are not going to hang out, is formed. Here's I'm going to go back. Yeah, we're still in the px orbital. Remember, a px orbital lays along the x-axis, and it has a nodal plane. You can see it like that. This atom also has a nodal plane for its px. When we bring them together in phase, we still have the nodal plane here, and we still have the nodal plane here. That's constructive interference. When we bring them in contact out of phase, we have the original node, and a new planar node as well, just to keep it exciting. So a new node forms. Now we call this the sigma star, or the antibonding orbital. Electrons in this orbital are destroying the molecule and tearing it apart. So we have a sigma 2px and a sigma star 2px, bonding and antibonding. Okay, so we've talked about the combination of the px orbitals from each atom. Those are the only ones that can combine on axes to form a sigma bond. But we still have the py and the pz orbitals, and we need to think about what's happening with those. So now we're going to move to the py, and on your paper that's showing straight up and down. I'm going to start at the bottom of the page to show the constructive combination. And that's when these are coming into contact with one another, and the same phases are going to overlap. So the red and the red, the blue and the blue, and they're going to make a new orbital that combines the in-phase region above the nodal plane and the in-phase region below the nodal plane. We still have a nodal plane in this orbital, so the py plane orbitals still exist. But now we have shared space up here, shared space down there. If you imagine they were Play-Doh, we kind of mush them together, and we now have a pi 2py bonding molecular orbital. It's pi because It was created by sideways overlap rather than head-on overlap. So sideways overlap gives us a pi. Valence bond theory told us it was a pi bond. Well, it is a pi bond, but it's now a pi bonding molecular orbital. That's in contrast to destructive interference, where they're not in the same phase. We still bring them close together, but they're like, stay away from me, and a new node forms. We still have the original node, but now we also have a new node, a new plane type node that's, when electrons are there, it's pushing them apart. Okay, so that was Py, and now I'm going to do this up out of the screen. Pz is coming straight towards you out of the paper. It's hard to draw that. It draws it diagonally, but really it's coming towards you like this. So it's just like the Py, but now it's that combination coming out of the paper. So we can have constructive interference, making a second pi molecular orbital. Now it's 2pz because it came from the z. Or we could have a destructive combination, but again, it's coming out of the page. And now we're going to have a new node form right here, but it's coming out of the page looking at you like this. So that's what we're trying to draw on our paper. So same phase comes together versus opposite phase. And we have a new node. It's just really hard to draw it in 3 dimensions, combining there. So now we get to put it all together. We start at the bottom, atom 1 on the left, atom number 2 on the right. We have our atomic orbitals on the left and the right. And we know as our S's combine, 2 atomic orbitals in, we get 2 molecular orbitals out. But now when we have 3 degenerate p orbitals, px, py, pz from one atom, and 3 px, py, pz from the second atom, when 3 plus 3, which is 6 atomic orbitals, come together, we're going to get 6 molecular orbitals. And the relative energies matter. When we have this is the one we're going to work with. Okay, so let's think about the sigma 2px. When we are combining these p orbitals head on, this has the most stable, the greatest overlap. So this is going to be the most stable, lowest energy orbital. That's in contrast to the side-by-side overlap. Even though they're bonding orbitals, they're side by side. It's not quite as stable. It's still a decrease in energy. It's more stable, but not as great as head-on-head overlap. Whether I combine on the y-axis or the z-axis, you can see that the combination is the same. So that's why we have pi 2py and pi 2pz. These orbitals are degenerate. They have the same energy because they're the same thing, they're just oriented in space differently. And then, however much an orbital goes down is the same amount of energy that its opposite is going to go up, at least for this story. So the anti-bonding for the pi goes up the same amount, but compared to the sigma, it went way down in energy. So the sigma anti-bonding goes way up in energy. I like to think of this as a relationship. So I am in a wonderful marriage. We are celebrating our 20th anniversary this May. We got married young, but we have a good marriage, and a wonderful marriage is a really great thing. It is very stabilizing, very wonderful. A very bad marriage is very awful, very, very destabilizing. In contrast, a good friendship is nice, stabilizing. A bad friendship, destabilizing, but hopefully you can, It's not as bad as a really bad marriage. That's how you can kind of think about it if you want. Or you can come up with your own analogy and tell me what you came up with next class. Okay, so we can put all these orbitals in, and then we get to fill them in. We're going to do the first filling right now because I want to kind of lock in this idea while we're here. Let's do this example for diatomic fluorine. Each fluorine starts with 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. That tells me I have 7 times 2, which is 14 electrons to place in my molecular orbital diagram. I'm going to count to 14, starting with the lowest energy molecular orbital. 1, 2, 3, 4, 5, 6, 7, 8. Notice that I have singly filled these orbitals. They're degenerate. I've lost count. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now let's calculate the bond order for fluorine. The number of electrons in bonding orbitals would be 2, 4, 6, 8 electrons. The number of electrons in antibonding orbitals, 2, 4, 6. I divide by 2. 8 minus 6 is 2, divided by 2 is 1. Fluorine, diatomic fluorine, has a bond order of 1, and that matches our Lewis structure, which is really nice because these theories go together, but we're going to see when we come back after the weekend that it can also correctly predict paramagnetism and diamagnetism when we get to the next example of nitrogen and oxygen, which is next class. All the best with your tests this weekend. I will see you on Monday.